so that when you supply the heat, what happens, the temperature of the object increases, so that there will be a increase in size of an object. Okay, depending upon the length, area and volume, we are going to define the expansion as linear, area or superficial, and volume or cubical expansion we call. Okay. Okay, fine. See you. Next, coming to this linear expansion, let us go through about what do you mean by this linear expansion. Okay, so coming to this linear expansion, you can see there, when a solid is heated, its length increases, then the expansion is called linear expansion. So that when you take any solid, okay, so that if you increase the temperature of that, what happens, the length of the solid increases. So this type of increase in length is called as the linear expansion we call. So let us come to the figure here. So you can see the first figure there, it is the length of an solid. Okay, the length of the solid is denoted by the letter L naught. Okay, that is nothing but, we say that it is before heating, the length of the solid is nothing but denoted by L naught. Okay, next let us say that you are heating that solid. Okay, if you are heating that solid, so what happens, the length of the solid increases. Okay, so the length of the solid after heating comes out to be as L is equal to L naught plus delta L. Okay, so what is that L denotes here? L is nothing but the final length of the solid, and L naught is the initial length of the solid, and that delta L denotes the increase in solid after heating. Okay, so L is equal to L naught plus delta L. L is final length, L naught is initial length, and delta L is the increase in length. Okay, once you are done, there will be increase in length, right? So that increase in length is denoted by delta L. So now we need to write in terms of mathematics, in a mathematical form. So for that, you can see here, in order to write in a mathematical form, consider a rod of length L naught. When the rod is directly heated, the increase in its length delta L is proportional to its original length. Okay, so you can see there, the increase in length of the rod, that is delta L, is directly proportional to the initial length of the rod, and it depends upon the change in temperature, and it is directly proportional to the change in temperature. Okay, so if you are supplying the heat more, what happens, the temperature of the object increases more. Okay, so that the expansion of the object will be more, so directly proportional. Okay, so hence the increase in length, that is delta L, of the solid or the rod is directly proportional to L naught and directly proportional to delta T. So combining this both L naught and delta T, you can write in the mathematical form, delta L is equal to L naught delta T. Correct? Delta L is equal, delta L proportional to L naught delta T. So in the next case, since here you are written in terms of proportionality term, in order to write in terms of equal, so what we are going to do, we are going to introduce a constant there. Okay, that constant we call that one as alpha. Okay, so hence delta L is equal to alpha L naught delta T. Okay, so delta L is equal to alpha L naught delta T. Take that one as equation 1. So the same equation 1 can be written as alpha is equal to delta L by L naught into 1 by delta T. Okay, alpha is nothing but equal to delta L by L naught into delta 1 by delta T, or simply you can write delta L divided by L naught delta T. Okay, so which is represented by the equation 2. Okay, if you ask that what do you mean by that alpha, alpha is called as the coefficient of linear expansion. Okay, alpha is nothing but the constant which we have added, right, and we call that constant as the coefficient of linear expansion. Okay, coefficient of linear expansion. So that the definition of alpha is, in terms of definition, you are going to define that alpha as, it is defined as the ratio of increase in length to the original length per degree rise in temperature. Okay. uh, the definition of that is nothing but, okay, if you are increasing the temperature of the rod by 1 degree Celsius or Kelvin, okay, so what happens, that increase in length is called as coefficient of linear expansion. Okay, that means that increase in length to the original length for per degree rise in temperature. Okay, and the SI unit of alpha is nothing but per degree Celsius or per degree Kelvin. Okay, so per degree Celsius or per degree Kelvin. So next, the length of the rod after heating. Okay, so how we are going to write the equation for a length of the rod once it is heated, after the heating. See, delta L, you know that delta L is nothing but L minus L naught, right? So by making use of this equation, what is that? L is equal to L naught plus delta L, right? So if you take out the delta L on the left hand side and if you move that L to the right hand side, so the same equation can be written as delta L is equal to L minus L naught. Okay, so that means that delta L is nothing but the increase in length. Increase in length is equal to nothing but final length minus initial length. Okay, so hence that L minus L naught is nothing but equal to alpha L naught delta T. You can write that one as L minus L naught is equal to alpha L naught delta T, or you can write that one as L is equal to L naught into 1 plus alpha delta T. Okay, so this is the equation 3. Okay, so L denotes the final length of the rod after heating. So this is an equation 3. Equation 3 denotes the equation of the, equation 3 gives the length of the rod after heating, that is the final length of the rod. Okay, so do one thing, just go through about this linear expansion in detail once. Okay, in case if you have any doubts, please let me know. Go through once, everyone. Yes, in case if you have any doubts, you can ask. Yes, Ashrit, superficial. Okay, superficial. We will come to that in the next class. Okay, so see here. Let me. I mean, we have left out with the 4 minutes. So before that, we will just conclude with today's topic what we have discussed. See here. So some of you were asking doubts regarding this Kelvin scale, right? So let me brief it once again. Okay. So as you know that the pressure of a the pressure or volume of a gas is directly proportional to temperature. Okay, the pressure or volume of a gas is directly proportional to temperature. So as you know that when you plot the graph P versus T or V versus T, what happens when you take three different gases, gas 1, gas 2, gas 3, you can see there in both the graphs P versus T and V versus T, as you increase the temperature, the pressure or volume of the gas keeps on increasing. Okay, so next, once you are decreasing the value of temperature, you can see there the pressure or volume of a gas keeps on decreasing. Okay, so as you keep on decreasing, what happens, the pressure or volume of a gas, the pressure or volume of a gas becomes zero. The value of pressure or volume of a gas reaches zero for a particular value of temperature, and that temperature is called as absolute zero. That is minus 273.15 degrees Celsius is called as absolute zero. Okay, so where pressure and volume of a gas value of that becomes zero. Okay, so in case if you go beyond that, if you decrease the temperature of a gas beyond that, what happens, sorry, if you decrease the temperature beyond that, what happens, the pressure or volume will take a negative value, which is not possible. Okay, so hence that is the least minimum temperature that can attain. Okay, so that the pressure and volume of a gas becomes zero. Okay, and that itself is called as absolute zero. Okay, so when you plot the graph, that is nothing but scales. Okay, in the case of Celsius scale, you can see there 273 minus 273.15 degree is nothing but we call that one as absolute zero. Okay, next in the Fahrenheit scale, in the same thing, say this is the temperature. In this case, what we have plotted, pressure versus volume, or uh, pressure versus temperature, or volume versus temperature. We have taken the temperature in case of Celsius. Okay, so the absolute value is nothing but it is minus 273. Suppose if you plot the same graph for taking temperature in terms of Fahrenheit, okay, the absolute value comes out to be for a value of minus 459.69. okay, so hence you call that one minus 459 as the absolute zero. Okay, next coming to the Kelvin scale. Okay, so in the case of Kelvin scale, the absolute zero is nothing but it is 0 Kelvin. It start with this scale. Okay, so in the Kelvin scale, the starting point, the starting value itself is nothing but this one, 0 Kelvin. We call this one as 0 Kelvin. Okay, so this is regarding the three different types of scales. Okay, and you have just come across this linear expansion, right? So any doubts you can ask. Sir, should we write starting notes? Okay, do one thing. Okay, just make a practice of this linear expansion. Okay, because in this chapter the numericals will be asked based upon this expansions. Okay, especially this linear expansion. Okay, so hence make a practice of writing this linear expansion. Okay, till that equation 3. Okay, just make sure